Let's get started with today's problem. The first problem of today is word break. This is LeetCode number 139, word break. Given a string s and a dictionary of strings word dict, return true if s can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Okay. Let's see. I've heard, because this happens to be one of the problems that I caught while just lurking in the LeetCode discussion channels of various Discord servers. I know that this is a dynamic programming problem, though I'm not quite sure exactly in what way is it dynamic programming. To a certain extent, it does make sense. Let's step away from dynamic programming for a second and just think about this in terms of recursion. Well, what do we actually have? In this case, for example, for our first example, we have the word LeetCode with our dictionary with leet and code. Seems straightforward enough. And we are trying to see if this string can be string separated, or it can be space separated into words containing only leet or code. Well, how could we solve this, or how could we break this into subproblems? My first thought is that, well, we need to break this down such that our subproblem is solving essentially the string, but minus one of the words. Let me think about this a little bit more. So if we go left to right, we can try to see if a substring that exists between 0 and our current index can build up a word which exists within our dictionary. If it does, great. If it does not, then that's fine as well. And this is sort of I guess you could say, is the more simple problem, right? Within this problem, that if we're considering just one word, then we basically run a linear scan through our word and see if it exists within. If we're talking about if it just exists within our larger string. So if a string is a substring of another string, then we would just run a linear scan and we would see if it exists within our larger string. So now the problem comes if we are dealing with multiple words that happen to be substrings. And this would be like in the case of example 3, where we could run left to right And when we run left to right, our first word that we create is cat, which is in our dictionary. However, when we add another one, we also add cats. In that case, which route do we actually take? I'm not sure if there's a way to say that we could take both, or we could only take one at that step, right? In this case, we would continue with first cat without s, and at the junction in which we create two possibilities, we have, well, two steps. We can either continue with a previous word, or we can start with a new word, right? And we really have those main two choices. We either have a word that we can continue, or a new word that we can start at this s. We can start with sand, or we can finish cats. We could theoretically take or keep those two possibilities, right? And if we keep those two possibilities, then we can continue with them. So the s would continue, considering this is index 1. See where this sort of prefix sort of exists within here. And then for the one where we add the s to the end of cats, we would start the new word at a, and the candidate for that would be the a here. And then we would continue with those possibilities until either we find no viable candidates, in which case we just terminate, we don't continue recursing on that end. Or we could continue if it does make sense, right? I think that's the strategy that we could go for in that case. But my next question then is, how do we check the substrings in a fast manner, right? Basically, let's see. We start with L. We find all the candidates. If starting a new string, find all candidates that start with the letter. Then check each individual character as we iterate through it. I think that makes sense. But where does the dynamic part actually come in? Where does the memoization part actually come in to speed this up? I'm not too sure at the moment. Well, let's see. I'm gonna start drafting some code to see if I can think of something. And if it doesn't pop up soon-ish, then this might be a solution where I have to probably take a look at the intuition part of a solution in order to really, in order to start to get an idea of what I actually want to do with this. So what we could do is that we will build a queue, and we can build this queue of, or do we want to build a queue? Yes. This will be an int, so this will be a queue. Int, it will be the indices within the dictionary to check against. So, let's see. So, at each letter, we can choose to either continue with an existing set of words or start a new word. This might end up being a recursive function entirely, with a string as a word dictionary, which is a list of string, an index, which is an integer, and this returns a boolean. And we can say s dot for each character. So how do we memorize this? I guess the main difficulty that I'm just having is just thinking of like actually the sub-problem that exists within here. Maybe the sub-problem is the sub-problem just the next string? Or not the next string, just the string with one less character at the beginning. So like if LeetCode is the string, is our sub-problem just eat code and comparing that against our word dictionary with the index at 1. With word break at string, word dictionary at index, index. Well, we'd have to match the word. Maybe match, if the word matches, then the subproblem is the string minus the word. So for LeetCode, we break it into a subproblem where s is equal to leet or s is equal to code. And that might work, but I think that makes sense. That's a subproblem that I can get behind. But where does the rest of that come from? Where does the rest of the intuition go? I guess the main thing is just I'm trying to think about sort of, okay, so we have the sub problem, which is the string without one of the correct words. Where does that take us afterwards? Well, first of all, let's think about how do we even match the word in the first place. And this might be a job for Kotlin here. Uh, Matches at. Ooh, that's a. Could we do a regex? I just want the pure documentation. So let's see. We could do a find. Well, what do we really care about here? Do we care about the order, whether we find it in the middle or on the sides or whatever? Um, what could we do? We could have this is like the most brute force of solutions, I think. We could have a queue of sub problems, I'll call them. And for each while queue of subproblems is not empty, so let's fill this with our initial string. For queue of subproblem, or not, we do word dictionary for each word. We will create a new regex. Val regex is a new regex of the word. Val substring is equal to regex dot replace. We'll replace our we'll say val front is equal to queue of subproblems dot first, and then we'll also do a queue of subproblems dot remove at 0, and we'll replace anything within our string. Actually, this is just Replaces all occurrences within the input string with the specified. Okay. With an empty string, if substring is equal or is not equal to word, so if the actual, if we had a match and it's something actually different, then we can do queue of subproblems dot add substring. And also, if substring is equal to empty string, then return true. So this indicates that we replaced all the values. And then, so the idea is that we go through the string, we go through the word dictionary every single time, right? So LeetCode, we go through Leet, we create a regex of the word, we replace all the occurrences of Leet with an empty string, so that leaves us with code that's not the same as the original word, so we add that into our queue. Same thing with code. So LeetCode, we are left with Leet, we put that into the queue because it's not the same. Next iteration, we start with code because that's the first thing that we added. Code and Leet, well, when we replace it, nothing happens, so we don't continue there. However, code with code, when we replace it, we're left with an empty string, and in that case, we return true. So in this case, we have potentially, let's see, let's do a runtime analysis of this. So in this case, well, when we are left with Leet, or when we start with the original string, we can produce up to n. So up to n items within each iteration, where n is the number of items in word dictionary, right? So potentially for each case, we could potentially produce up to n substrings, assuming that all of them have some sort of match, right? And each iteration runs n times because we take each iteration runs through n items. So we have n items per iteration, and we have to run through n items each time. So that seems like that's leaning towards O of n squared. But I feel like there's probably something hidden in there that's making the runtime not as fast. Because this sure as hell isn't dynamic programming yet. Of course, we do have a subproblem, which is just the word minus the first occurrence, but it feels like this O of n squared would be reserved for the dynamic programming solution. It feels like something is missing within my runtime analysis. Well, at least we could say that the space will be up to O of n. It will be up to O of n and not O of n squared, because our queue at the most will be filled with n items, and at that point we would start, when we take the item out, we can only produce one regex substring that goes in. So up to O of n space Are there overlappings in the space? So what I mean by that is that is there an overlap between items? of subproblems. Within a dynamic programming problem, there should be overlapping subproblems. So now I'm starting to think whether or not there are potentially cases where our substrings are the same. Would that even be possible? That our substrings end up going to a point where they reduce to the point where they are essentially the same? Well, let's see about this one. I'm gonna do this in comment space. If we take out the cats in cats and dog, we get an dog. If we get rid of dog, we get cats and. If we get rid of sand, we get cat og. If we get rid of and, we get cats og. And if we get rid of cat, we get sand og. Well, some of these are quite similar. Cat and catsog are, of course, quite similar. Andog and sandog are quite similar as well. I wonder if there's a way here then to consider to optimize this in such a way that I guess we take the result from minus cat, and if there is an s, but let me think. Is there something that we could do with that? Well, what if we break this down further? If this doesn't match with cats or cat, we get og if we do a minus and. We get and if we do minus dog. Do we get something similar here? If we do minus sand, we get og. If we do minus we get sand if we do minus dog. We get sog if we do minus and. I think that those are the only applicable ones. So we do see some overlapping subproblems. But how do we get to this point, right? How do we get to this point? With our overlapping subproblems, and how do we memorize it, right? I guess that's the main thing. Because it seems like we would need I think naively we could produce a hash map. We could call this substring map is a mutable map of string boolean. And we can create a var here. Has substring. It starts off as false. if we add something, then we can say has substring is equal to true, and string or substring map dot add or get our substring is not null, or it's either null or substring map get substring is equal to true. Actually, only if it's null. Or substring map get substring is equal to true. Then we return true. Once we get out of here, we can say if has substring is equal to false, then what we do is that we can do substring map dot put our substring we can put our string maybe, rather our front, false. Basically this means that this substring or is bad and shouldn't be pursued if it happens to exist in here. So the idea is that we do a sort of top-down type thing, I think, where we sort of say, okay, we'll start with the strings, we'll break them down into subproblems. If we don't know about the string so far, actually this part really isn't needed. If we don't know about the substring, the status of the substring, we can explore it. And if a substring does exist, that we haven't explored yet, then we can go and explore it. If we've checked all of the substrings that we have here, or rather, if we haven't produced any additional substrings for this string, then we can say that this string is done. We've explored all of it. We couldn't find a proper match, and therefore any additional matches should not go through. So basically, if we have one in our queue, we should just disregard it. That saves a little bit of time in terms of actually investigating the bad strings, but I don't think it actually changes much in terms of the asymptotic runtime. Let's go ahead and run this code first, and let's see where we're at. Maybe if we spell substring correctly. Oh, I didn't check if there are any other compiler errors. Ooh, are we gonna get a TLE? Interesting. Oh, we want to do front here. Whoops. Okay. Let's throw in a submit and see if we're actually fast enough to actually pass this. If not, we've hit the 30-minute mark, and I think starting from now, I'm going to make an executive decision to, if I cannot solve this within 30 minutes and I do not have any ideas of what the optimal solution looks like in terms of how to improve it further, then I am going to start looking at the solution much earlier now. I think my goal is to look at the solution and learn from it, and hopefully if once I've seen enough of these solutions, I sort of start to get a feel for them in the future. This is something that I'm personally a bit conflicted about because of the fact that it feels like giving up. It feels like you're not really like learning anything. But at the same time, when I think about how I learn in college, as I am currently, I don't just bang my head against problems, right? I actively go and seek help. Looking at a problem and thinking about it for a while does help, but within the context of something that is new or something that I am completely lost on, that is where I think finding help is the most beneficial. So I think that it does make sense for me to sort of think about this in a different way. However, I am going to do a little bit of print testing here for this one. I am interested in seeing sort of like the substrings that get produced out of it. So we can do print line string front, print line produced substring, and let's see sort of what we did. So this should produce at the highest level andog, sandog, catsog, or catog, and catsog. And then andog should produce og and an. So andog, catsan. So andog is minus cats. Right, and then catsan, catog, catsog, and sandog. And then andog produces oh, interesting. It's producing a substring which is the same. Okay. I guess we'll do this and see if this works. It looks like this equality operator just wasn't working. Oh, was I assigning it? No, not equals to. Okay, no. Oh, no. Is not equal to front. So the substring that we get is not equal to the original one that we put in, not the word. The word doesn't matter. The word should have been fully replaced. This will never be true. Okay. Okay, looks like that actually goes through now and it isn't just bad for no reason. Let's just run through the other example test cases. I imagine that this is still incredibly slow just because of all the leftover stuff. Just because of all the leftovers at the end, the leftover values that we just have to iterate through in terms of the words. Ooh. Let's see. Why do we get this wrong? Because it's not, when we replace it in the middle. Okay. So we probably do have to go left to right. Um hmm. If we do a find, Huh. A find gives us a match result, but the match result that gives us an int range. We'll do a find. So this should do the first one, starting at 0. If the substring, if the result of this dot range dot start is 0, so if we find it on the left side, then we can say substring or regex replace first of the input front to nothing. So the idea of this is that if we find it on the left side, then if we find it on the left side, we can create a substring of it and then continue on. Because the words kind of have to be contiguous, don't they? Let's see. How do we bring this into it? The substring map substring. Well, we can say if substring or val substring is equal to regex.replace first front to that. And we can replace this here. Idea of this is that first we check to see if we found something the match result well, if substring is not null, first of all, right? Because this is a nullable match result. I'm assuming that if it doesn't find anything, then it returns null. Yeah, if there's no matching string, then the find method returns null. So first we check if it's not null. And that is started at the beginning, at the left side of our substring. Then we'll say find. That shouldn't do anything, or that shouldn't affect anything. So if we find it at our left edge, then we do the substring. If the substring is, after we replace it, is nothing, then we return true. We found we're done. And otherwise, if it is not null, or if it is null, so if we haven't explored the substring yet, then we can take this substring and add it into our queue for exploration, and then we pass it off further. Let's see if this actually works. Okay, so that works. Let's run through the other tests. looks like they worked. Let's take a look at this. Okay, cool. So we got the TLE. Awesome. Okay. And it is 45 minutes in, so we went 15 minutes over, but it's time to take a crack at the solution. So I'll take a look at it, and I will be back. Yeah, so this is the top solution from the discussion tab. This recursion sort of, the brute force solution sort of, to a certain extent, is quite similar to my solution. Sort of just breaking down and checking to see if it contains, if the word works, and if we can, and also if it exists within, or if the substring of that also works. The interesting thing is that they use this I, and this I serves as basically the starting point for their substring. So they don't just start, they don't just keep it at 0. They keep on pushing it forwards, and they basically grab all the substrings possible, which I think is interesting. Then they do a little bit of an optimization by memoizing the results from the previous, which is something that I tried to do but didn't quite accomplish. So let's check out the Java solution and let's see what we could do, right? And let's just walk through the Java solution together. So this is the actual function, the base function that's called. They create a new boolean array, which is the same size as the string itself. Interesting. Let me think. So they create a new boolean at there. And I guess the point is to say that the substring starting from this exact index, is it possible, basically? Which I think is interesting. Looking at the private, the secondary method that they did. So they create an integer n, which is the string's length. And if we're starting at the, or if our integer, so if our starting point is at the length of the string, then we return true. So I guess that's like if we finished if we got to that point, right? That makes sense, sure. If we already know what the value is at that point, then we just return the same thing. And then we check the rest. So this is the, I guess, where the n squared runtime comes from. Not sure about this n cubed. I guess this substring counts as part of it, and then this also counts as part of it. So both of these are nested within here, which is why that happens. But what does this actually do? So we start at the next index from our current. And first of all, if we have the substring and we do the word break. So the word break here would only be well, it had to return true, right? Then we set this to true. Okay, so if we have, if our substring is valid, and so this is for our current. So if we take our current word, and then the substring starting at the substring that starts after the word ends is also valid, then we return true, right? Because then we know our section, our word is for sure valid, and then our substring is valid, therefore this new solution is valid. Otherwise, if we don't find anything special, then we return false and set that value to false, because even if the substring, or even if we find our word, our substring subsequently is not true. So I think this makes sense. I am still a little bit confused about how this solution is O of n cubed, though. I think it makes sense for it to be O of n squared. Let me think about this a little bit more. So we're iterating through from there. And the worst case scenario is if we had just one string and then a character like A, right? We just had a long string of A's like that. So what would we do in that case? Well, we would start with that one. We're not at the end. We don't have a valid value. And therefore, we will check each value. Obviously the substring works. And then we'll call word break on them. So we call word break on the substring that's shorter. So that'd be n plus n minus 1 plus n minus 2 plus n minus 3. So that'd be n squared right there. So the inner calls are n squared, and we go through each word. So that's n times n squared, so that's n cubed. I think that I'm understanding, if I'm understanding that correctly. So I think that's why it's n cubed? Okay, interesting. And I guess final thoughts before we jump back and actually code it up in Kotlin. I think I was kind of close to the solution. I think I briefly mentioned that the subproblem could either be one smaller or smaller than the word. And it looks like in this case it's really the smaller than our current sort of word. I think we got close to the solution. We just didn't quite get the recursion part right, because we still stuffed a lot of dead values into our queue without actually having sort of I'm not sure if our hash map sort of thing actually worked in terms of memoization. So let's actually go back and let's code this up in Kotlin. I don't think it'll look significantly different, but we'll give it a shot. So we'll put this here, and we'll say own solution too slow, and we'll start here. Word break at index. It will be an index, which is an int, s, which is a string, word dictionary, which is a list of strings. And we'll say that we'll create a global variable. So we'll say val I'm trying to think of a descriptive name rather than just doing DP. We'll do DP for now, though. We'll do boolean array of size s.size. Actually, s doesn't exist yet. We'll do a private late init var DP. which is of type bool array. Is bool array actually a thing? Or boolean array rather? Okay, we could do a boolean array. Yeah, cool. But this starts off as false, whereas this solution actually uses null for a very specific reason. And that is to see if we have visited that actual node. So what we could do instead is we'll create a list of type boolean nullable, right? And dp is equal to list. Can we create a list of a specific size? I feel like I've asked this like many times before. I'm not sure if we actually can. Where's the init? Yeah, okay. In that case, we will do a... So we can't use a... We can't define the size, right? I don't think that there's an implementation that lets us do a size. Let me just double check the source. Where is list of defined? I don't have time for this. Okay. We'll just do a weird implementation. We'll do a mutable list of boolean question mark for I in 0 to s dot size minus 1 dp dot add null. And then we'll do return word break at index 0 string s word dictionary. So this should fill up from 0 to s dot size length string minus 1 inclusive of both sides of this dp. And then we can say that if dp at index is not null, return dp at index. And if index is equal to s dot size, return true. It's a little bit weird, IMO, to compare index to size when it realistically shouldn't ever hit this, but not quite too sure about that. So we know about those two. And then we can say for I in index plus 1 to s dot size minus 1, we can say if s.substring starting at index, or rather I, to, sorry, index to I. And if this is contained in the word dictionary, and if our word break at index I, so starting at our new index, and we do standard stuff, so we do S and our word dictionary. If that is true, then return dp index is true. This is an interesting way to put it, right? So dp at this index is true. Otherwise, return dp index is false. So this should set it and then also return false, if I'm understanding it properly. So recurse on the substring if we have a match at the left-hand side starting at index. Returning true if if our substring is also valid. Return false if our substring is not valid. Okay. So let's think. So our word break, we create a DP array of booleans. If it's not null, then we just return that value. That's fine. We should do this first, because otherwise we might hit an array out of bounds exception. We always want to compare the index first. So if the index is equal to the size, in this case because this goes to size -1, so this word break at index could potentially go to size. I see, so that's why we do is equal to size. Okay. Because we're starting at index +1. We're always starting at 1 after in order to actually have a valid string. I guess the substring for Java, I haven't used substring in a very long time. I'm guessing substring for Java is left inclusive, right exclusive. So if you have it at the same character, then it's not valid. Then it'll just return an empty string rather. Okay. So, and then we used our dynamic programming memoization to check that if we've already calculated a value, we just return that. It doesn't really matter what it is, as long as it's not null, right? Because it's initialized at null. Then we check, starting at the substrings, we just check each one. And if we have a substring from starting at our original value to this whatever index it is, this right-hand index, if this is a valid word within our word dictionary, and then the rest of the string is also valid, then we can say that our current one is valid. And if not, if all that is still, if that just goes through and none of the words word combinations are valid, then we return false. So this is this is an interesting one. I want to say top-down type of recursion, because we're starting at index 0, and then we make all of these calls, all of these nested calls to the base, all the way down to essentially the base cases, right, if they're valid. And then from there, once we hit the bottom, then we slowly build up our solution. I think that's top-down. I think so. But that's not too important. at least for this case. Um, so yeah, we've built our dynamic programming, our list of nullable booleans. Um, we fill them initially with null, then we check if it's the same. If our index is at the end, then we return true. We've hit the end. We don't need to go any further. If our index is not null, if we've already explored the substring, then we can just return whatever was there. We check through all of the indices starting from our current index all the way to the end. In the worst case, this could potentially be, or at least in the first case, this is O of n, right? In the worst case, let me think actually. We are doing this, yeah, from index all the way to size minus 1, yeah, so this could potentially be O of n. If our word dictionary contains the word at the left-hand side, and our subsequent substring is also valid, then we return true. Straightforward enough. This word break at index could potentially be called on each one. So that would be n calls n minus 1, n minus 2, so on and so forth. So that summation goes to n times n minus 1 divided by 2, which is O of n squared. So this whole thing is O of n cubed runtime. In terms of space, this is O of n, or I guess, it depends on, we have to define n now. N is defined by, we can say n is defined by, and I guess maybe O of s would be more, honestly, more descriptive. O of s, where s is the length of our string. This word dictionary contains is O of n, where n is the number of words in our word dictionary, times s, where s is the length of our string, I think, because we have to check each character pretty much in the worst case scenario. And then our word break here is O of s squared, and this entire thing is O of s. So it really depends if n is larger than s, which one would dominate, but I think for the moment we could probably say that the string will probably be larger, and in that case it would be O of s cubed. Space is O of s because we're just storing one boolean per index in the string. And yeah, I think that's about it in terms of the solution. Let's give this a run, and then let's give this a submit if everything is fine. You are not happy about this because DP is a property that could have changed by this time. Size is not valid because this should be length. DP at index. If DP index is not null, return DP index. Well, we know that this is not null, so let's just do a double exclamation mark operator there. We can do this manually by doing this and then just returning true. Or this should be false. Seems like Kotlin is not a fan of inlining that, at least for now. Or at least in 1.3. Okay. I think that's all valid. The only thing that isn't valid is this function. Mutable list of. Wish there was a way to build it up in a different way. I think there is a generic array type, right? Array boolean of size s.length. And we can just do null. I think there is, if I recall correctly, there is a generic array type in Kotlin. Awesome, cool. Let's just toss in the example cases. Ooh. Whoa. Something went wrong there. Interesting. I was expecting that to work, but given the other case, but this is not working out. Interesting. Let's see why not. This is returning false. I don't think the substring will be different. Substring. In Java, you can take, okay. You can take the substring after. But we don't have a delimiter. Do we still have a substring method? I assume that we do, right? Oh, we can just do a substring from the index then. Well, let's see. Let's see what this actually is. Oh. If I do I instead, I think is okay. Inclusive, exclusive, yeah, that's correct. Oh, we do need this this end. Because we're only taking that sliver of string. Interesting. It's definitely not our for loop. If it contains that. Oh, interesting. It goes until this E right here. This E never gets called. Huh. There, but E is Where did I go wrong? It does include that one? Why does it include the one at the length, though? Surely this would cause an issue, right? Oh, it's exclusive. I'm stupid. Oh my gosh. Okay. It's exclusive. I forgot about that. Okay, now the example cases should pass. And now we can throw in the submit. So watch out for this. We need our substring is exclusive. And yeah, I think this is actually decently well commented. I think I can understand the solution that was provided here. I think it does make sense, their process, and I honestly think that my hash code or my hash map solution probably could have worked. I might work on it a little bit more after this, just off camera if I do have time, because I really think that I was actually pretty damn close to the solution. I just was missing some parts. But yeah, in any case, I hope you learned something, and I'll see you for the next problem.